Electricity is the flow of electrical charge. It's a fundamental force of nature and the backbone of modern technology. To understand electricity, there are several key concepts to grasp, including voltage, current, resistance, and power. Voltage, often described as electrical potential difference, is the force that drives the flow of electrical current. It is measured in volts. Think of voltage as the pressure in a water pipe. The higher the pressure, the more water flows. Similarly, the higher the voltage, the more electrical current will flow through a circuit. Current is the rate of flow of electrical charge. It's the amount of charge passing a given point in a circuit per unit of time. Current is measured in amps. Using the water pipe analogy, current is the amount of water flowing through the pipe. A higher current means more charge is flowing. Resistance is the opposition to the flow of electrical current. It's measured in ohms. In a water pipe analogy, resistance would be like a constriction in the pipe, making it harder for water to flow. Higher resistance means less current will flow for a given voltage. Ohm's law is a fundamental relationship between voltage, current, and resistance. It states that voltage equals current times resistance, or volts equals amps times ohms. This law is crucial for analyzing and designing electrical circuits. For example, if a circuit has a 12 volts power supply and a 6 ohms resistor, the current flowing through this circuit would be 12 volts divided by 6 ohms, which equals 2 amps. Power is the rate at which electrical energy is transferred or used. It's measured in watts. Power equals voltage times current, or watts equals volts times amps. Understanding power is important for calculating energy consumption and selecting appropriate components for electrical circuits. A basic electrical circuit consists of a voltage source, a conductor, and a load. The voltage source provides the electrical potential difference that drives the current. The conductor, typically a wire, provides a path for the current to flow. The load is the component that consumes the electrical energy, such as a light bulb or a motor. There are two main types of electrical circuits: series circuits and parallel circuits. In a series circuit, components are connected one after another along a single path. The current is the same through all components in a series circuit, but the voltage is divided among them. The total resistance in a series circuit is the sum of the individual resistances. In a parallel circuit, components are connected along multiple paths. The voltage is the same across all components in a parallel circuit, but the current is divided among them. The total resistance in a parallel circuit is less than the smallest individual resistance. Understanding these fundamental concepts is essential for working with electricity safely and effectively. Always remember to follow safety precautions when working with electrical circuits. Turn off the power before working on any circuit, use insulated tools, and never work in wet conditions. Electrical safety is paramount to prevent shocks, burns, and other hazards. When designing electrical circuits, it's important to select components with appropriate voltage and current ratings. Overloading components can lead to overheating, damage, and even fire. Consult datasheets and follow manufacturers' recommendations when selecting components. Grounding is another important safety measure in electrical systems. Grounding provides a low-resistance path for fault currents to flow back to the source, tripping circuit breakers or fuses and preventing electrical shock hazards. Ensure that all electrical equipment is properly grounded according to local electrical codes. Circuit breakers and fuses are protected devices that interrupt the flow of current in a circuit when it exceeds a safe level. Circuit breakers can be reset after tripping, while fuses must be replaced. These devices protect electrical circuits from overloads and short circuits, preventing damage to equipment and reducing the risk of fire. Electrical codes and standards, such as the National Electrical Code, or NEC, provide guidelines for safe electrical installation. These codes specify requirements for wiring, grounding, overcurrent protection, and other aspects of electrical systems. Adhering to electrical codes is essential for ensuring the safety and reliability of electrical installations. Alternating current, or AC, is a type of electrical current that periodically reverses direction. It's the type of electricity used in most homes and businesses. Direct current, or DC, is a type of electrical current that flows in one direction only. Batteries and electronic devices typically use DC power. Understanding the difference between AC and DC is important for working with different types of electrical systems. Transformers are devices that change the voltage of alternating current. Step-up transformers increase the voltage, while step-down transformers decrease the voltage. Transformers are used to transmit electricity over long distances at high voltage and then reduce the voltage for local distribution. Capacitors are electronic components that store electrical energy in an electric field. They are used in circuits for filtering, smoothing, and energy storage. Inductors are electronic components that store electrical energy in a magnetic field. They are used in circuits for filtering, energy storage, and creating oscillating signals. Diodes are semiconductor devices that allow current to flow in one direction only. They are used in circuits for rectification, voltage regulation, and signal processing. Transistors are semiconductor devices that can amplify or switch electronic signals. They are used in a wide variety of electronic circuits, including amplifiers, oscillators, and digital logic circuits. Integrated circuits, or ICs, are complex electronic circuits fabricated on a single semiconductor chip. They contain millions or even billions of transistors and other components. IC are used in computers, smartphones, and many other electronic devices. Digital electronics deals with circuits that process digital signals, which are represented by discrete voltage levels, typically 0 volts and 5 volts. Digital circuits are used in computers, microcontrollers, and other digital devices. Analog electronics deals with circuits that process analog signals, which are continuous voltage or current levels. Analog circuits are used in amplifiers, filters, and other analog devices. Microcontrollers are small, programmable computers on a single integrated circuit. They are used in embedded systems to control devices and appliances. Sensors are devices that detect physical quantities such as temperature, pressure, or light and convert them into electrical signals. They are used in a wide variety of applications, including industrial automation, environmental monitoring, and medical devices. Actuators are devices that convert electrical signals into mechanical motion. They are used in robotics, automation, and other applications where controlled movement is required. Power supplies are circuits that convert AC voltage to DC voltage. They are used to power electronic devices and appliances. Inverters are circuits that convert DC voltage to AC voltage. They are used in solar power systems, uninterruptible power supplies, or UPS, and other applications where AC power is required. Electrical motors are devices that convert electrical energy into mechanical energy. They are used in a wide variety of applications, including fans, pumps, and vehicles. Generators are devices that convert mechanical energy into electrical energy. They are used in power plants and other applications where electricity is generated. Renewable energy sources, such as solar and wind power, are becoming increasingly important for generating electricity in a sustainable way. These sources rely on electrical engineering principles to convert renewable resources into usable electricity. Electric vehicles, or EVs, are becoming more popular as a cleaner alternative to gasoline-powered vehicles. They rely on electrical motors, batteries, and power electronics to provide propulsion. Smart grids are advanced electrical grids that use digital technology to improve efficiency, reliability, and security. They incorporate smart meters, sensors, and communication networks to optimize the distribution of electricity. Understanding the fundamentals of electricity is essential for anyone interested in pursuing a career in electrical engineering or related fields. With a solid foundation in these concepts, you can explore more advanced topics and contribute to the development of innovative electrical technologies. Remember that safety should always be your top priority when working with electricity. Take the time to learn about electrical safety practices and follow them diligently to prevent accidents and injuries. Learning about electricity can seem intimidating, but by breaking down the concepts and understanding their relationships to one another, it becomes much more approachable. Start with the basics of voltage, current, and resistance and build your knowledge from there. Practice applying these concepts in simple circuits to gain a better understanding of how they work in real-world applications. There are many resources available to help you learn more about electricity, including textbooks, online courses, and hands-on projects. Take advantage of these resources to expand your knowledge and skills in this exciting field. The world of electricity is constantly evolving, with new technologies and innovations emerging all the time. By staying curious and continuing to learn, you can stay ahead of the curve and contribute to the advancement of electrical engineering. Firstly, always prioritize safety. Secondly, start with the basics. Thirdly, practice applying the concepts. Fourthly, take advantage of available resources. And fifthly, stay curious and keep learning. Understanding electrical concepts opens doors to various career paths. You could work in power generation, distribution, electronics design, telecommunications, or automation. The skills are transferable across many industries. Consider pursuing certifications or degrees in electrical engineering or related fields. Formal education provides a structured learning environment and validates your knowledge. Look for internships or entry-level positions to gain practical experience. Hands-on experience is invaluable for developing your skills and building your resume. Network with other professionals in the field. Attend industry events and connect with people on LinkedIn to expand your network and learn about job opportunities. Remember that learning electricity is a continuous process. There's always something new to discover. By staying committed to learning and developing your skills, you can achieve your goals in this dynamic field. The applications of electricity are virtually limitless. From powering our homes and businesses to enabling advanced technologies, electricity is essential for modern life. By understanding the principles of electricity, you can contribute to solving some of the world's most pressing challenges such as climate change and energy security. 1. Always use appropriate personal protective equipment, or PPE, such as safety glasses and insulated gloves, when working with electricity. 2. Inspect electrical equipment and tools regularly for damage. 3. Never overload circuits or extension cords. 4. Be aware of the location of electrical panels and shut-off switches. 5. Know how to respond to electrical emergencies, such as shocks and fires. Electricity is not something to be feared, but it is something to be respected. By following safety precautions and using common sense, you can work with electricity safely and effectively.